Hello, everyone. Welcome to another ConsenSys Cypherpunk Hackathon workshop. Today, we'll be with Patrick going over layer 2 overview, basically. It's going to be a really good workshop today around this topic. Quick housekeeping around Crowdcast, which is the platform we're using today. On the right-hand side, you see the chat area, which you can feel free to chat here during the workshop. If you have any questions, you can put them here. However, also, we would love you to add them to the Ask a Question queue at the bottom. That way, Patrick can see if there's any questions that he can pause to answer. We'll also leave a little time at the end for Q&A as well. If you do type something in the chat and then you put a question mark, before you hit enter, you'll notice a little orange button will pop up and say, would you like to add this to the queue? So that's a neat way to add the questions there too. Also, we have, this will be available for replay, as mentioned in the comments, at the exact same link, which makes it nice and convenient. And we'll also post this on the ConsenSys Hackathon 2021 channel. So please join us there if you're not already in that channel. We'll post all the latest replays, any workshops to RSVP still for, as well as the sign-up form for the actual hackathon. We're doing the team building now. So if you have ideas, if you want to hack, if you've never done it before, it doesn't matter. We'll help you put together a team. We'll help you get in there to win some prizes. So also, just if you've always wanted to hack on an idea, and this is your chance to really to let it loose. So without further ado, I'll hand the mic over to Patrick.
Awesome. Thank you very much, Shay. I guess there's a slide here for an overview about me. So I'm basically I made a joke here, I'm a Mooncat enthusiast out of Fura. But historically speaking, before I came to ConsenSys, I was the CEO of AnyDot, which has now later become ITX. And prior to that, I was an assistant professor at King's College London, and I did my PhD in Bitcoin and Ethereum. And I mostly focused on layer 2 protocols and blockchain scalability. So it's actually really exciting now to see some of them come to life and evolve and, start getting used. So what I really want to cover today is an overview of layer 2. And I'm probably going to deep dive into some topics. So this is more of a technical talk with some, nice high-level overview around it. First, I'm going to talk about, why do we even care about layer 2 protocols? And then I'm going to talk about off-chain payment channel networks, so something like the Lightning Network. Because really, back in 2015, that's all we had. That was the first example of a layer 2 protocol. And then later on, we had these commit chains, and I'm going to talk about why they're awesome and why we should all be excited for the rollups. Now, these slides are sort of like a work in progress, so I think they're mostly finished. But I don't know how long it's going to take, so I hope I do it within 90 minutes. And if not, I'll hopefully skip some content. So as everyone here is aware, cryptocurrencies do not scale. Historically speaking, Bitcoin could support 7 transactions per second, and Ethereum could support around 12 transactions per second. It's a bit better now, but it's a small magnitude of what we need for a global permissionless computer. And the problem is that once we go above that threshold of 7 TPS or 14 TPS or 15 million gas, the fees go from 0 and then they just skyrocket. And over the years, we've slowly seen this build up. So back in 2020, January 2020, Ethereum fees were about $100,000 a day. You even have a Bitcoin maxi here, Grubbles. I'm sure some people know him. Even he was complaining that Ethereum was so popular that the fees were more expensive than Bitcoin. And then they continued to get more expensive. By June 2020, Ethereum was hitting $1.2 million fees. And now it's $60 million fees / $100 million fees. It's actually it's crazy how expensive fees are now on the layer 1 network. But that's mostly because, people are going to pay high fees with the I'm going to send a transaction that'll cost me $100 if I think I'm going to make more than $100 with those transactions. So, they're profitable transactions, and there's a reason why people will send them and pay these crazy fees. But why do we have these fees? What are the bottlenecks? Why can we only support 14 transactions per second? And really the issue is that, it's a peer-to-peer network. We send a block every 14 seconds. We send transactions to the network. And ideally, every single peer in the network should be able to verify the blocks and transactions in real time. And so scalability hinges on these 3 different components. The first is data. we just have to send data across the network, transactions, blocks. That's more of a bandwidth bottleneck. There's storage. So the whole point of the blockchain is that by re-executing every transaction, I can create the same database that everyone else has. This is the layer 1 database. And performing state updates in that database is a bottleneck, and that's called state bloat, which is, I think, currently our biggest bottleneck on Ethereum. Then afterwards is computation. When I send a transaction out to the network, or when a miner sends a block, I have to re-execute every transaction, update my database, and then pass it on. Computation is a slow process, and is also another bottleneck of trying to get blocks across the network in real time. And one question could be, well, why don't we just increase the TPS of Ethereum to 55 per second? And this is what they've done on Binance. And the issue is that when you increase the TPS, we hit the bottlenecks, and not every peer on the network can keep up, verify blocks and transactions in real time. So here, PancakeSwap is 2,000 blocks behind the Binance blockchain. Another example, their API was reset because their blocks were syncing. And that's a great example of us hitting the bottlenecks. Binance Smart Chain is a good example of why we just can't simply increase the TPS. And what the real bottleneck is the scalability. And what impact is this having decentralization? Well, really is a trade-off between throughput and public verifiability. So on Binance, you can do 55 transactions per second. We can have low fees for the most part, and we can have a large user base. But that comes at the cost of the computational resources or your hardware setup to validate blocks in real time as they appear. On the other hand, on Ethereum and Bitcoin, we're optimizing for a large set of validators. So more peers in the network can validate transactions in real time. So you really do have this sort of trade-off between throughput and public verifiability. So now that we understand, we do have these bottlenecks, we care that everyone on the network can validate blocks in real time. We simply just can't increase the throughput ceiling. With all that in mind, how can we scale the network? The easiest solution is the centralized approach. This chosen one, they're just appointed, they produce blocks, and there's no competition. And this is sort of how we've scaled over the past couple of years. So if you've used Binance, Coinbase, Bitstamp, if you've ever deposited funds into an exchange, you've technically used the chosen one centralized approach to scalability. I lock funds into Coinbase, I perform my transactions, then I withdraw my coins back to Ethereum. That is a scalability solution, but the problem is it's custodial. I'm effectively locking my funds up into a custodial system, a custodial ledger, and this single sequencer can fully freeze, confiscate, or they can lose my funds. The worst part is as well, it's not publicly verifiable, it's not auditable. The layer 2 database in this case is opaque. I can't verify if Coinbase is running a fractional reserve. I have no idea if they have my funds. But the really exciting part is these custodial ledgers offer an amazing user experience. There's low fees, and actually a lot of the time you don't have to learn anything about crypto, which is why people still keep their coins in these systems. But of course, it's used every day, but it's custodial and it's high risk. By 2016, it was said that 33% of Bitcoin exchanges had been hacked. And when they get hacked, there is quite a large scale hack. In 2016, Mt. Gox lost, there was 2014, they lost 850,000 Bitcoin. Bitfinex in 2016 lost 120,000 Bitcoin. So we're locking our coins into the scalability solution, but it's fully trusted and is actually very high risk. So we don't want to have the centralized approach. That isn't very exciting. The next one is, well, what about sidechains? Why don't we just move the traffic from Ethereum to another blockchain? And one thing I want to say about a sidechain is that a sidechain is just an independent blockchain network. There's another blockchain network out there, for example, Polygon, Doge, Bitcoin. They're all sidechains. They're independent blockchain networks. They exist and they process transactions. And really, there's a bridge that connects Ethereum to the sidechain. So we want to, have Bitcoin. There's RUP Bitcoin, Rent BTC, DBTC. These bridges all have their own trust assumptions. They don't rely on Ethereum for security. They don't rely on Bitcoin for security. They rely on, for example, a multi-sig or some exotic, proof of stake system. But, Bitcoin's not dependent on Ethereum, and Ethereum's not dependent on Bitcoin. the risk of using that bridge is isolated to that bridge. So this is one way you could scale the network. But the issue is that, one, we have to trust that other independent blockchain network. And two, we have to trust the bridge that brings us towards that sidechain, or that other blockchain. And so then there's two risks here, depending on how they're implemented. So the security of the funds relies on the bridge and not really the consensus protocol of any blockchain network. So again, we're going to cross that out. We're technically scaling by moving the traffic elsewhere, but we're not really scaling Ethereum. We're just taking traffic off Ethereum, and we don't get any of the nice things that Ethereum gives us. There's other ways you could, scale the network. So one is, well, why don't we change the blockchain network? Why don't we implement a DAG? I think Ava's done that. Or why don't we implement sharding, where we have several different blockchains and we shard computation across them? For now, there are valid ways to scale, the throughput of the network, but then you hit that public verifiability dilemma still. So we can increase the TPS, but, not everyone can validate 55 transactions per second in real time. So we still hit that bottleneck of public verifiability. So what this talk's going to focus on are layer 2 protocols, which we're all really excited for. And the idea is that we can take transactions, move them away from Ethereum, have the parties here, involved in that application execute it locally amongst themselves, and then periodically we just, touch base with Ethereum to say, this is what's happened on the layer 2 protocol. And there's two ways to achieve this. One is a payment channel, which we're going to explore very soon. It mostly works for two parties. And the other one is a commit chain, which is basically these layer 2 ledgers, like, Arbitrum, Optimism, Starkware, ZK Sync. And as we're going to see, they're both different layer 2 style protocols. And hopefully someday they'll work in conjunction with each other, and we'll all be excited for our layer 2 future. And by the way, guys, if there's any questions, you can just also drop them in the chat in case, I explain something and it's not obvious what I'm saying. So layer 2 protocols, why should we be excited for layer 2? So the idea of a layer 2 protocol is that, at least for the commit chain case, it's a dependent blockchain network. So it's still a blockchain network. It still has a consensus protocol. It has its own smart contract system. It has account balances, but it's no longer independent. Okay? And that's because it relies on the layer 1 blockchain, the settlement layer, for its funds. So the basic idea is that I'm on Ethereum. I lock funds into the layer 2 protocol. I transact on the layer 2 protocol as much as I want. Now, when I want to take my funds from the layer 2 system back to Ethereum, the layer 2 protocol has to convince Ethereum that every single state transition, anything that's ever occurred on the layer 2 network is valid, it's not compromised, and everything is Safu. And once Ethereum is convinced that no fraud has occurred on the layer 2 system, it will then accept the withdrawal transaction and it will send the funds to me. So really, the layer 2 protocol has to convince Ethereum that everything is valid. And if something's not valid, then basically, we'll talk about that later. But if it's not valid, then the funds that are locked in that layer 2 system become frozen and they get withdrawn back to the layer 1 system, or they get rejected. We'll talk about what happens in that case later. But that's the big difference. Sidechains are independent, layer 2 systems are dependent. And this dependency will really determine, how much of a layer 2 protocol are you. And that's basically the small point to make there. Sidechain, layer 1 doesn't care about the sidechain at all. There's some independent bridge. And the layer 2 protocols, the layer 1 must be convinced that everything is valid about the layer 2 protocol before it will deposit or allow funds to leave the layer 2 system. And how does this bring us to scalability? Well, we're still going to do the good old trick of, let's take transactions from Ethereum and put them on another blockchain network. That's basically what these commit chains are trying to achieve. It's off the Ethereum chain, but it's on another chain. So I've got the big bold arrows there. The transactions go to these rollups, but very few transactions come back to Ethereum. And that's basically how we scale, the compute, the data, and the storage. It's all on the layer 2 network. And Ethereum doesn't have to worry too much about, all the transactions that are happening there. And why are layer 2 protocols exciting? Well, there's one transaction to join the off-chain protocol, i.e., I go on Ethereum, I lock up my funds, and then they'll pop up and they'll be released on Arbitrum, Optimism, Starkware, and payment channels, whatever. Now that I'm on the layer 2 network, I can transact as much as I want because, we don't care as much about public verifiability there. I can transact as much as I want there. There'll be low fees, etc., etc. And once I'm done, I can take my funds and bring them back to Ethereum. And I only have to trust Ethereum. It's up to Ethereum to make sure that my funds are safe, and I don't have to trust a human or a third party. So it's actually a really exciting way to scale the network. And as we'll see with some of the commit chains, you can actually start doing some funky wizardry and magic tricks to really bring down the amount of work that's needed to verify that it's correct. And that's also a really cool scalability solution. So the question is, can we really move all three resources, data, storage, and compute, to the layer 2 system? So this is what we're going to find out today. So we're going to start with layer 2 protocols. Okay, we started with layer 2 protocols, sorry. We're now going to move on to payment channels. And hopefully for the next 30 minutes, we're just going to focus on payment channels. So payment channels typically involve two parties. They're called Alice and Bob. And both parties can lock funds into the system. So Alice will lock one coin, and in this case, Bob's not going to lock any coins. Now they get locked into the channel, and now the idea is that once we've created the channel, Alice and Bob will agree that Alice has one coin and Bob has 0 coins. And now if we want to perform a transfer, we can do this in an off-chain manner that does not involve Ethereum. Basically, Alice and Bob will both send a message to agree upon the transfer. So how does this work? When Alice sends one coin to Bob, Alice will sign this and give it to Bob. And then Bob will sign it and give it back to Alice. And when both parties have exchanged signatures, in the naive case, they've both agreed that Bob now has the one coin and Alice has 0 coins. And basically, that's how a payment channel works. There's two parties sending messages and going back and forth locally between themselves. And it looks like this really cool little animation here. And that is how you do transfers in a payment channel. And what's really exciting here is that every single transfer is local between Alice and Bob. Ethereum, the layer 1 blockchain, is never involved in any of these transfers in the optimistic case. So everything is kept off chain. The data is kept off chain, the compute is kept off chain, the storage is kept off chain. It's a bit like having a box, you lock in coins, then there's a piece of paper next to the box, and we just agree how do we distribute the funds between both parties. That's a really exciting way to scale the network. But then the question is, we have to make sure that everything's secure and Alice and Bob can always get their funds back. So let's just say Alice has one coin, Bob goes offline, can the funds get stuck? And ideally, no, as long as there's this property called balance security, an honest party can always withdraw the agreed balance from the channel via an on-chain dispute. So ideally, what Alice will do is Alice will, send a transaction to Ethereum and say, Ethereum, Bob is offline. I want to withdraw my funds, and this is the latest agreed balance that we had. Now, Ethereum is going to trigger a dispute process or a challenge process, and it has a fixed period of time. And it's going to wait around until Alice has submitted evidence and for Bob to submit evidence. Bob has, let's say, 3 hours to submit evidence about the latest state of the channel, aka the balance that he thinks, what's the best way to phrase it? Okay, Alice will send a dispute to say, according to Ethereum, the last thing me and Bob agreed was that I have one coin, Bob has 0 coins. Ethereum will wait until Bob can provide evidence, and Bob has 3 hours to do that. Bob could then submit evidence to say, no, Ethereum, Alice is wrong. The real balance is that I have one coin and Al has 0 coins. But if Bob doesn't respond within 3 hours, then the dispute gets resolved, the channel gets closed, and Alice is sent her 1 coin. So that's really cool. The way to think about this is more like a court settlement layer. You know, there's a dispute, there's evidence. When the challenge gets resolved, Ethereum will look at both pieces of evidence and it will send the funds based on, you know, the most convincing evidence. So that's how a payment channel works at a very high level. And actually, the evidence is really easy. Every time you send a message, you can commit a counter. And whatever evidence has a has counter, our largest counter is considered the latest state. You know, I don't really want to explain that here. Well, maybe I do in a future slide. But over the years, you know, this was mostly iterated on in Bitcoin from 2013 to 2015. We had Spielman channels, we had replaced by time lock, we had replaced by revocation, which is currently how Lightning's implemented. But what's really frustrating is that when you consider payment channels for Bitcoin, it's sort of like you're constrained. You're really trying to build these payment channels, but they're just really awkward. You would never really want to implement them. Of course, people have because it's the only way to implement it. But Bitcoin was never designed with layer 2 or off-chain protocol design in mind. And in the Bitcoin world, they've got the kitchen sink or a hammer, and they're really forcing Bitcoin to make this work. Because of that, the design is very convoluted. It's very confusing. You don't really want to explain it on a slide. Although I could later if someone's interested. And then on Ethereum, these get called state channels, you know, and there's various state channels. I think it's, I don't have Magmo here actually, but Magmo is currently implemented by ConsenSys. And the idea there is that, you know, state channels can be more expressive than just payments. And we can talk about that shortly. But the basic idea is that, you know, payment channels are the ultimate layer 2 in off-chain protocol, as in everything's off-chain. The blockchains only consult with the open channels, settle disputes, and close channels. So this is really cool. Now we have a different, you know, mindset of how the blockchain works. You know, Ethereum, this layer 1 system, is a settlement and arbitration system. It's optimistically, Ethereum never has to worry about transactions on the layer 2. It's the ultimate last resort if the layer 2 system breaks down. You know, and it forces all parties to remain honest and stick to their word. So that's how a payment channel works as a very basic component. Now, there's one feature of a payment channel I want to highlight, and it's called the conditional transfer. Now, can we perform a conditional transfer? Now, this is going to look really stupid to begin with. And after I explain it, you'll wonder, oh, why would anyone ever think of this protocol for? But as we'll see soon, this is the basis of how the Lightning Network, you know, works. So what is the humble conditional transfer? Well, Bob is going to generate a secret R, he'll hash it, and he'll give the hash to Alice. Then what Alice is going to say is, Bob, if you reveal the pre-image of this hash, you know, the secret of this hash before time t, you get the coins. And optimistically speaking, Bob will reveal the secret, Alice will get the secret, they'll both cooperate, you know, they'll remove the condition, and then Bob will get, you know, the 1 coin. So the idea here is that Alice can buy the pre-image of a hash, a secret value, in a way where both parties don't have to trust each other. Now, what happens if, Alice is, sent the conditional transfer, Bob revealed the secret, and then Alice doesn't cooperate with the last step? Well, if Alice doesn't remove the condition, then Bob has until time t to settle the dispute and resolve it using the layer 1 blockchain. How does he do this? Well, he waits around for Alice to cooperate. Alice doesn't cooperate, and then he reveals the conditional transfer and the secret R to Ethereum alongside Alice's signature, although I haven't got the signature there. The Ethereum, or Bitcoin in this case, will say, okay, I've got the conditional transfer, I've got the evidence, it confirms that Bob has revealed the pre-image R before time t, Alice agreed to these conditions, hurrah, Bob is going to get the coins. And that's really cool. So now in this layer 2 system, we have a mechanism to enforce fair exchange. In the optimistic case, Alice and Bob can, Bob can sell the pre-image R, and Alice can buy the secret in a way where both parties don't trust each other. If it breaks down for whatever reason, there can be an on-chain, dispute, and it can be settled, and Bob can always enforce that he gets the one coin for selling the secret. Now, it's trust-free in the sense that Alice and Bob don't have to trust each other, they only trust the blockchain. And it guarantees that Alice will always transfer the payment if Bob reveals the secret. Now, the big issue with this is mostly called the American call option. So the idea is that Alice has a fixed time period, 1 to 2 hours, or sorry, I think it should be Bob. Basically, one party has 1 to 2 hours where they don't have to reveal the secret. Bob says, I'm going to sell you the hash. Alice commits to the payment. Bob can wait around for an hour and say, oh, well, actually don't want to sell you the secret now. I want to give it to someone else. And that may not sound like a problem in this basic example, but later on it becomes a problem if you want to do DeFi or trading, because now you basically get a price quote that lasts 2 hours, which isn't the ideal world for selling tokens. And it's free to do that as well. So that's how the conditional transfer works. So now we have payment channels. We have this conditional transfer. We have a way, that to sell a secret. This now results in the HTLC. And basically, the question comes up, what if we had a network of channels? So right now, we've only considered two parties in one channel. What if you had a network of channels? You had hundreds and thousands and tens of thousands of payment channels. Well, that is the Lightning Network. It has, when I took this screenshot a few years ago, it had 31,000 channels. And now what's really cool is that if Alice has a channel to Bob, Bob has a channel to Caroline, and Caroline has a channel to Dave, then actually we can do a path-based payment from Alice to Dave. And in a way, what we're doing is we're synchronizing a single payment from Alice to Dave across the network. Such that Alice sends a coin to Bob, Bob sends a coin to Caroline, and Caroline sends the coin to Dave. Then it's all over. And remember, Alice and Dave don't have a payment channel together. Alice has a channel with Bob, Bob has a channel with Caroline, and Caroline has a channel to Dave. But Alice can still pay Dave in a way where no one has to trust each other, and none of the transactions ever hit the blockchain. This all remains in the layer 2 world. And off-chain and locally amongst the parties. So I actually took this out of my slide. Typically, I would explain how that synchronization works across the 4 channels or 3 channels, but I don't think it really matters for this talk. I just want to highlight that you can synchronize payments from Alice to Dave, even though they don't share a payment channel. And that'll hopefully become useful later on. So just remember that, the Lightning Network or payment channel networks are good for synchronizing value transfer across a network of peers or a path of peers. It's not very good for payments, and that's what we're going to figure out now. So now what we're going to do is we're going to move on to the commit chain world. Okay? So, payment channels are for 2 parties. Commit chains, the whole point of the commit chain is to try to create a new ledger or, a central party where I can access this website, this service. I can do transfers, but I never have to trust the central party. Now, before I get into commit chains and how they work and how they're designed, what I want to do is to take a look at payment channel hubs. Because back in 2016, back in 2017, this was how we thought they could be designed. So you have this non-custodial operator, and you have this big pot of money, a big pot of Bitcoin in this case. Yeah, I've got a real Bitcoin picture there. That's how cool I am. Then Alice comes along, hi Alice. What Alice is going to do is create a channel with the operator. And she's going to the operator is going to deposit 2 coins into this channel. Now, what's important to highlight is the operator has 2 coins and Alice has 0 coins in the channel. Bob comes along. Hi, Bob. Now, Bob's going to create a channel with the operator. Bob will lock up 2 coins, and the operator will lock up 2 coins. Caroline comes along. Hello, Caroline. Carlin will lock in 1 coin, and the operator will lock in 0 coins. And finally, Dave comes along, and the operator really likes Dave, so the operator locks in 4 coins of Dave, and Dave doesn't have to put up any coins whatsoever, because he's such a cool guy. Now let's take a deeper look at this scenario. So the issue is that 1, Carlin can only send coins. She can't receive any coins on the service. Carlin can send the coin to the operator, but the operator has no funds in the channel, so you can't send any coins to Caroline. The other problem for Alice is that Alice can receive coins, but Alice can only receive up to 2 coins. Once the operator sent the 2 coins to Alice, that's all she can receive. And she'll have to spend the coins again, in order to receive another 2 coins. Now, the other issue is that the hub, this, payment channel hub, the hub needs to take their own money, their own coins, and lock them in the channels with their users. And there's an opportunity cost here, because I could lock 10 coins in with Dave, but Dave never does a transaction. Dave never receives any coins. Thus, I've locked in 4 coins, and they've not made me any money, because I'm not facilitating any transfers. So typically, when people were trying to build these payment channel hubs, Dave would have to come along and pay for the privilege of opening a channel with the hub. And this was a screenshot I took 2 years ago for the capacity of the channel that you could have. And the worst thing as well, overall, is that the hub has a hot wallet. All these coins are live and active in the payment channels. They're hot wallets. So it's hard to become a big, good big hub unless you've got a very secure setup. And the worst thing of all is, in order to join this layer 2 system, in order to use the operator as a central point for facilitating transfers, every customer has to open a channel via the layer 1 blockchain. So there's always an on-chain transaction in order to join the layer 2 system. And that sucks, imagine you have a friend, you're like, yo friend, come play with my layer 2 system. I want to send you some coins. Then they have to go get Bitcoin. In this case, they have to get Bitcoin. They have to put it on the main chain. They have to open a channel with the operator. And after about an hour, because it's a block every 10 minutes, they can finally, receive a transfer via Lightning. That is a terrible user experience. It's just that's the most, it's a terrible way to onboard new users. So, payment channel hubs are great because 1, there's instant finality. When, Alice gets the 2 coins from the operator, it's basically, final in the sense that you can always redeem the coins right away. So you can redeem them to the layer 1 blockchain and then, go away with the funds. And there's no trust. But the collateral lockup doesn't make it permissionless because not everyone can be a hub. To be a hub requires upfront collateral and a lot of collateral to be a very good hub. And over the years, what we've seen is that they're just not very practical to implement. And so what happens is that all these layer 2 Lightning wallets, they're all custodial. There's Blue Wallet, there's Zebedee. Zebedee's for games and it's for small value, so I appreciate, that can be custodial. And LN Strike is also a custodial wallet. And now what we have is, I joined this layer 2 Bitcoin ecosystem, and really what I've done is I've joined this custodial ledger that's run by this company, and then this custodial ledger has a connection to the Lightning Network that will allow me to send funds to another provider. So I go from Blue Wallet to Strike. Blue Wallet's custodial, they do a Lightning payment to Strike, and then on Strike, I receive a custodial balance. And, there's nothing wrong with this. This is, what is wrong is that, they're custodial ledgers, they're good user experience, they're good for, a small set of funds. But that's because payment channel hubs don't work. And so you have to build a custodial ledger if you're building anything that's customer facing. And on the back end is really the Lightning Network doing this instant routing value transfer. And so on BTC LN today, what we mainly have are custodial ledgers, and you have the Lightning Network, in the middle. This really awesome, exciting routing network. This is how you can tell them a Bitcoin Maxi. Then you have Bitcoin as this base settlement layer. But this is a barrier to adoption. Custodial ledgers. The Lightning Network is a routing protocol for synchronizing across ledgers. That's why we have the conditional transfer. That's why Alice can pay Dave. What you're really doing is synchronizing value transfer across a path. And adoption's slow because you have to rely on Coinbase, BitMEX, basically the CeFi, the integrate with Lightning, and then make it really easy for me to jump from Coinbase to BitMEX. I'm on Coinbase. I want to, perform some trade on BitMEX, Lightning across, trade, Lightning back. Well, that's the ideal world. But they're custodial ledgers, and a lot of these companies don't have a large incentive to implement this. And that's why, adoption is quite slow there. But what if we could, build several open, permissionless, and self-custody ledgers with DeFi? What if I instantly want to transfer, transfer value from ledger X, I'm on ledger Y, I transfer the ledger X, I perform a swap, and I come back to ledger Y. What if I could do this in a way that's like nearly, I don't want to say instant, but very, very quick, without bypassing the layer 1 blockchain altogether? If you have these ledgers that, prioritize self-custody of funds, they're secure and people can build upon them, and you have these DeFi layer 2 ledgers, then actually now you have this payment channel network to route between them. So you can bypass Ethereum altogether. I don't know if that sounds a bit blue sky or crazy, but we are now getting these really awesome permissionless self-custody ledgers. We have Arbitrum, Aztec, Starkware, ZK Sync, Optimism, Stellar, ZK. I said ZK Sync already, sorry. Polygon, ZK Swap, Loopring. These ledgers are evolving now that prioritize self-custody of funds and allowing people to deploy and run smart contracts on them. And what we've seen with Connex in the past couple of weeks, because Connex is a payment channel operator, as far as I'm aware, they have a payment channel between Polygon and some other, layer 2 ledger. I actually forget now what the other layer 2 ledger is. But there's sign of uptake, sorry. You can see here over the months that last month they did $8 million in volume back and forth between the ledgers. And they were able to bypass Ethereum for this. And now they're actually having liquidity issues. So what happens is, it's a payment channel. They send all the funds to Polygon, but now there's not enough traffic going backwards back to, let's just say Optimism in this case. So all the funds go from Optimism to Polygon, but they need bi-directional traffic for really this payment channel to be, routing efficiently. So I think what they just released today or yesterday was a rebalancing protocol to rebalance the channel, such that, all the funds end up on one side. You can rebalance it so they're both, it's a bit like a level, so they're balanced again. You can then start doing transfers back to Optimism in this case. But that's really exciting though, because finally payment channels are being used for routing between ledgers, and that's the whole point of why they're useful. And that's actually the big issue we had for like 3 or 4 years. We're all really excited for these layer 2 protocols. We have payment channels, we have payment channel hubs. We could build this routing network, but we had nothing to route between. There were no other ledgers to route, and now we're getting the ledgers. So I think that's why I'm really mega excited for all of this. So now the question is, at last, how do these commit chains work? So what I'm going to explore is, I want to explore the commit chains from first principles to better understand rollups and more generically commit chains. What is a commit chain? How does it work? What is the wider environment? What are the assumptions? Who is the adversary? What is their power? What are the security goals that must be satisfied before I roll up a secure? What does it mean to be secure for a layer 2 ledger? And then you'll be set up for the rest of the hackathon. What I should mention is that this part of the deck is still a work in progress, by the way. These slides typically take me months to make. And every talk I give, I sort of iterate on them over time. So they're quite good, but I think in 6 months' time they'll be much better.
This is great, Patrick.
Sure,
Just
don't bother me.
Sorry. Oh, sorry, didn't mean to scare you. No, I was just saying, even though your slides may seem streamlined, they're great. This is you're doing great in terms of the subject matter here.
Awesome, cool, yeah, awesome. Okay, I can just continue there. Sorry. So where was I? So now we're going to talk about commit chain. So what is a commit chain? Well, the idea is that you have a sequencer, and the sequencer's job is to collect these layer 2 transactions. Periodically, what they're going to do is post a checkpoint to Ethereum to the layer 1 blockchain. This checkpoint will have a list of transactions, or at least a commitment to a list of transactions and the new ledger state. And ideally, given the list of checkpoints, anyone in the world should be able to get these checkpoints, get the data, and recompute the layer 2 database themselves. And ideally, Ethereum, the layer 1 blockchain, it's the layer 1's blockchain job to be convinced that the layer 2 database is correct, valid, and it's not compromised. So basically, you have the sequencer, Alice is there. Alice will deposit one coin into Ethereum, and it will be unlocked in the layer 2 system. It's a bit like depositing coins in Coinbase. You deposit coins, then you get an active balance or positive balance on Coinbase. So once Alice has a balance on the layer 2 system, Bob comes along. Hi, Bob. Alice will sign a transaction that will send one coin to Bob, and she'll give this to the sequencer. The sequencer can notify Bob that he's going to receive one coin. But remember, he's going to receive it, but he hasn't yet received it because the transfer has not been finalized. The sequencer has acknowledged that they've received the transaction. Then the sequencer will wait around for more off-chain transfers. And there's no more on-chain transfers because I didn't want to make any more slides for that. So what will happen is that the sequencer will get Alice's transfer, stick it in a checkpoint, and broadcast that checkpoint to Ethereum, and then it'll be sent to the layer 1 blockchain. And periodically, this is all the sequencer does. They collect layer 2 transactions, and they post checkpoints to Ethereum. And as I mentioned, anyone in the world should be able to get the list of checkpoints, fetch the transaction history, and recompute the layer 2 database themselves. And then they can be convinced that the layer 2 database is correct, that they have indeed received the coins, and that nothing's compromised and everything's valid. But now the question is, what does it mean to be secure for a commit chain? And there's this really good tweet thread by Georgius that always pops up once in a while. What he says is that layer 2 security should equal layer 1 security. And what I would argue is that this is too ambiguous as a definition. By layer 2 protocols cannot be the same as layer 1, but they can get pretty damn close. And as this, closeness, it's really what makes it a layer 2 protocol. And what you'll learn is because it's close, there'll be a spectrum of different solutions to this. So what does it mean to be secure? Well, first, what we need to, remember is, what are the protocol assumptions? What do we assume to be true? What's the threat model? Who is our adversary? And what are their special powers? How can they try to break the system? And finally, what are the security properties? What are we trying to keep secure? And hopefully, at some point, I'll have some good comparison of all the layer 2 protocols deployed, but they're not in these slides yet. So let's get on the protocol assumptions. So what we assume for these commit chains is, 1, the layer 1 blockchain is neutral infrastructure. It's independent, and the block producers are financially rational. So what I mean there is that Ethereum is neutral. It's not colluding with the sequencer or the layer 2 protocol. What we assume is that there's a consistent view. So every single party has access to Ethereum and has access to all transactions on Ethereum. So Ethereum is like this bulletin board. Everyone can look at the bulletin board and have a consistent view of the same data. That's what we assume. We assume there's eventual delivery. So if a user wants to send a transaction to Ethereum, as long as the user pays a reasonable or an appropriate network fee, that transaction will always be mined within n blocks. So basically, if I want to send a transaction to Ethereum, I can always do that and no one can stop me. We assume the smart contracts are trusted third parties with public state. They are immutable and they cannot be compromised. The reason for this is that when I join the layer 2 system, there's a layer 1 smart contract that I will deposit funds into. When I deposit my funds into this smart contract, I can only get my funds out when the smart contract is convinced that everything on the layer 2 system is correct and valid. So this smart contract, we get a lot of things for free with it, but we have to assume it's trusted everything's public and it's free of bugs. But that really does control, deposits and withdrawals and everything to do with security of the layer 2 system. And finally, because we care about blockchain scalability, we have to assume the parent blockchain, Ethereum, the layer 1 blockchain, has limited computation. It just it has considerably less computation than the layer 2 network, because otherwise it's not a scalability solution. So we have to assume that it's like a computer from the 1970s. It's very slow, it's very expensive, and it can't do a lot. Now, what about the adversary? Who's the adversary for these commit chains, these layer 2 protocols? Well, we assume the adversary can control the message flow control in the layer 2 system. So if Alice is sending transactions or messages on the layer 2 system, the adversary has full control. They can view, order, drop, and censor all messages on the layer 2. We assume the adversary cannot interfere with Alice sending transactions to Ethereum or the layer 1 system. So everything on layer 1 is secure and safe, and the adversary can't do anything. On the layer 2 system, the adversary has complete control over the message flow control. What we also assume is that the adversary can corrupt nearly every single party on the layer 2 system. The only party that adversary cannot corrupt is Alice, the honest party, and the layer 1 blockchain, which is Ethereum. Otherwise, everything's corruptible, everything can be taken over. The adversary has full control over that. Now, what I've described is basically the most powerful adversary possible. They control all messages, they can corrupt all parties. The only thing they can't break is cryptography or Ethereum. And as you'll find out over throughout this talk, or as you investigate these layer 2 protocols, not all layer 2 protocols are the same, and not all layer 2 protocols can constrain or outright defeat this adversary. And they will make stronger trust assumptions because they can't defeat it. And that's fine, because we're getting close to layer 1, but we can't be layer 1. We still have to fight this adversary in order to do that. And another way to look at it is that you have this layer 1 smart contract, you have an honest user, they're both working together to fight the sequencer, to constrain the sequencer, and to make sure that the layer 2 protocol cannot be compromised. And if you don't have this epic fight in your hands, then you're just not a layer 2 protocol. You're something else, but you're not layer 2. So security properties, what does it mean to be secure for a layer, a commit chain, a rollup, etc., etc. So the first one is the data availability problem. So remember, what the sequencer has to do is post checkpoints to Ethereum. And the checkpoint is typically the hash of the ledger state and the list of transactions. And given the transactions in the previous state, you executed and you recompute the new state of the layer 2 database. There's a commitment to that stored on Ethereum. Now, how do we guarantee that the transaction history for the layer 2 ledger is publicly available? So one, we can check that the checkpoint's correct, but there's also other reasons why this is necessary. One is auditability. Given these checkpoints and the transaction history, I can recompute the layer 2 database myself, and I can verify that everything's correct. 2, for interaction. If I want to transact on a layer 2 system, let's say it's Uniswap, and I want to swap, token A to token B, I want to know what the exchange rate is at this given time. And the only way I know the exchange rate is if I have a copy of the layer 2 database. And finally, withdrawals. If the user wants to leave the system from layer 2 to layer 1, typically Alice would have to prove, Mr. Layer 1 smart contract, this is my balance on the layer 2 system, and I want to withdraw my funds from the layer 2 system. So the user has to convince Ethereum and convince the layer 1 smart contract what their balance is on the layer 2 system before they can withdraw their funds. The only way you can get that evidence and prove it is if you have the data where you can say, okay, according to the layer 2 database, this is my balance, and then Ethereum can verify that. So you actually need it for withdrawals as well. Now, there are 3+1 approaches to solving this problem. The first is 1, we can trust an authority or committee to provide this data. So for every new checkpoint, there'll be a committee who will provide a digital signature and say, yep, I received the data and I promise to serve it to users when it's requested. So I'll say the Starkware volume approach. We trust a committee for this. The second approach is to wait for data availability. I won't talk much about it here, but this is how Plasma Cache works. It's actually one of the only real solutions to the problem, but it only works in special circumstances and it's not really practical. The third one is an on-chain challenge. So every time there's a new checkpoint, there's a dispute period where any user could say, sequencer, make this data available on the layer 1 blockchain. Then the sequencer would have to respond and make that available. Now, the issue with that is if there's a challenge process, the sequencer can get griefed. You could have 1,000 users challenging the sequencer every round. Now, the sequencer doesn't have to pay for this necessarily. You can have every time a user issues a challenge, they put a security bond next to it, and then that'll refund the sequencer for answering the challenge. But it just becomes this rigmarole of, we need security bonds, we need challenges, there's a fixed time limit, we need to extend the time limit. And so far, no one's ever, I guess I should say the rollup community are not convinced is a realistic solution to the problem. I think it's a fine solution, but I'm not implementing it, so that's why. Then the final solution is bingo. What is a rollup? Well, all transaction data is rolled up and posted to the layer 1 blockchain. And this is a new trust assumption. We have to assume that the layer 1 blockchain has plenty of bandwidth and it can propagate all transaction data that is required for recomputing the layer 2 database. It's one of 4 ways to solve the problem. It's the easiest way to solve the problem. But now we've already had a stronger trust assumption. We assume that Ethereum has plenty of bandwidth, and that will soon become our bottleneck for scalability on Ethereum. So what about the state transition integrity problem? What does this mean? Well, this is all about protecting the layer 2 database and its integrity. So what the sequencer could do is post a new checkpoint with a state, and then in the list of transactions, there's an invalid transaction. And obviously the sequencer would want to do this because if the sequencer can include an invalid transaction, they can change the database, send the sequencer all the funds, and then the sequencer can simply steal all the funds and withdraw back to Ethereum. So really we want to make sure every single transaction in the layer 2 system is valid and it cannot, it's not being compromised. Bingo, again, this is optimistic versus zero knowledge proofs, fraud proofs versus validity proofs. Now, fraud proofs and optimistic rollups, the idea here is that the sequencer is making an assertion. So when they post a checkpoint, they are asserting that this checkpoint is valid. They're basically putting their money where their mouth is. They say, here's the checkpoint, is valid. And now there's a 2-week period where anyone can come along and they could challenge it and tell Ethereum, that checkpoint is not valid. Here's the invalid transaction. So in the fraud-proof world, the sequencer will assert that something is true. Then there's a challenge period where anyone in the world could then challenge that and try to convince Ethereum that it's not true. And there's 2 different fraud-proof systems so far. The first is the non-interactive fraud-proof. So if the sequencer posts a checkpoint and it contains an invalid transaction, the user could then basically post evidence of this. What they'll do is they'll say, Ethereum, transaction 20, I'm going to dispute this. What I'm going to do is I'm going to recreate the state on Ethereum just before this transaction is executed. And then Ethereum will re-execute that transaction, and then you'll have the post state. And then Ethereum will compare the post state with what is inside the layer 2 database. And they'll do that using Merkle trees and proofs, etc. But basically, Ethereum's going to recompute the invalid transaction, and then it will verify if the layer 2 database is correct, according to the checkpoint. That's the non-interactive approach, because all the user has to do is, send transactions to recreate the state, send the transaction to execute, and then send evidence that compares what we computed with the layer 2 database, or at least what was claimed to be the layer 2 database. The issue there, of course, is that state could be expensive to recreate, the transaction could be expensive, and then doing that comparison, that evaluation of the post state can also be a very expensive process. But it's non-interactive, and you can just send them sequentially. The other approach is the interactive fraud proof. So this is where the sequencer will post a checkpoint, and then the challenger will, say, oh, one opcode in that checkpoint or in that list of transactions is invalid. So the challenger and the sequencer, they'll perform a binary search on Ethereum. They'll find the disputed opcode, and then Ethereum will simply evaluate that single opcode. And then obviously if the opcode is invalid, then it will just reject the checkpoint. So the non-interactive fraud proof is optimism, and the interactive fraud proof is arbitrum. And it's really cool actually that they've both gone down different routes and how they implement these fraud proofs. But the real difference is just how granular is that fraud proof challenge. The non-interactive approach is at the transaction level. The interactive approach is at the opcode level. And that's basically the really cool insight for those fraud proofs. Now, the last thing I want to mention is when you post a checkpoint, there is this challenge period. So off-chain, anyone, running on, but I'm participating on Optimism or Arbitrum or Optimistic Rollup, when the sequencer posts the checkpoint, I can verify off-chain that everything's correct, everything's valid, and I'm content. But it's going to take 2 weeks until Ethereum's convinced that there is no fraud. And thus, for those 2 weeks or that week, your funds will remain locked until that challenge period has been processed and finished. The zero-knowledge approach is more wizardry. So the idea is that when I post a checkpoint to Ethereum as a sequencer, checkpoint, post, they also provide a proof that the checkpoint is valid and all state transitions are correct. So there's no assertions. There's no, I assert that this is true. There's only facts. There's the checkpoint, there's the proof. It's factual, it's objective. Ethereum will be immediately convinced that the checkpoint's correct. Now, the issue with the zero-knowledge proof approach is one, expressiveness. It's still not yet possible to do generic smart contracts, although they're working towards that. So I know ZK Sync has the ZK EVM that uses wizardry to get towards it. But then the second problem is proving time. So depending on the circuit and the wizardry that you're doing and the type of computation, that proving time can just explode because it's not very, compatible with the ZK approach. The other problem is, so that's to do with, programming environment and then creating the proof. The other problem is when we send the proof to Ethereum, one, the proof has a certain byte size. It can be pretty big. And two is verification time. Ethereum has to verify every single proof. Oops. And, Ethereum, and we have to pay for that. So I'm trying to remember the numbers now, but, if a proof costs 500K gas, for example, then it doesn't really make sense to, post a checkpoint until you have a minimum number of transactions such that it covers the cost of sending the proof as well to Ethereum. So, there's two different approaches for this, but that's actually, optimistic rollups and the zero-knowledge rollups. This is the main thing or main topic or security property that everyone talks about. But then, while that's the main focal point, all the other security properties sort of get ignored. And no one really studies them or looks at them. And actually, sometimes the other security properties are more important than fraud proof versus EKP. Well, hopefully we'll see soon. So, sorry for the tangent. I know that was quite long. So the next question is withdrawal integrity problem. So the question is, how can I withdraw my funds if the sequencer does not cooperate? Basically, Alice will say, sequencer, here's my withdrawal transaction, please include it. The sequencer will reply and say, nope, never, your funds are stuck forever. If the sequencer is being nasty and doesn't let you process your withdrawal transaction, how can you get your funds back out? And withdrawal integrity is sort of intertwined with protocol liveness. So the first one could be, we just guarantee the commit chain can never halt. Anyone can be a sequencer, and anyone can post checkpoints, etc., etc. Although that comes with its own bag of problems. The second one is, well, why don't we use the layer 1 blockchain to force state transitions? So anyone could post their layer 2 transaction to Ethereum, and then Ethereum will, force this transaction to be processed later on. So, the idea is that Ethereum forces the layer 2 transaction to be executed. And that's actually a really cool way to solve the problem. The third approach is on-chain exodus, it's been called. I think that's the phrase ZK Sync use. So the layer 1 blockchain needs to be convinced that the layer 2 protocol is compromised or halted. It's no longer live, it's no longer progress, and there's no more transactions being posted. And so all users will just withdraw their funds based on the last valid state of the database. So I have $10 on the system, sequencer disappears, there's no new checkpoints, then eventually Ethereum will just let me withdraw my $10. Now the problem with withdrawal integrity is that if you only consider, if the rollup only performs transfers, then it's really easy. Everyone has an account balance and I can just withdraw my funds. If it's a smart contract platform and there's smart contracts on the layer 2, then for me to withdraw my funds, I need to unwind my positions in the smart contract. So if I'm an LP in Uniswap, I need to get my funds out of Uniswap into my account, and then I can withdraw my funds. And so really the only good solution to this is to force state transitions via the layer 1 blockchain. That's probably the ideal solution for this. So to summarize, there's really 3 security properties that matter for these rollups or commit chains. Data availability, how do we guarantee all the data is available? 2, state transition integrity. How is the layer 1 blockchain convinced that all transactions on the layer 2 system or blockchain are valid? And finally, withdrawal integrity. How can an honest user be guaranteed they can always withdraw their funds from the system? Now we can solve all of these problems, and hopefully we can slay the beast, defeat the adversary, and deploy a secure layer 2 system. I've got a little Ethereum shield there. This is from the Bear Wheel in 2014. We can satisfy all 3 properties. Then do we still need to trust the sequencer? And of course, the answer is going to be yes, no, yes, no, yes, no. Because one, it'll depend, it'll depend on how well we have solved those security properties. As I mentioned, there's 3 security problems. We can get close to solving them, but we don't always outright solve the problem. But 2, there's other problems that pop up. So the first is order fairness and extractable value. So remember, the sequencer, their only job is to order transactions and post them to Ethereum for them to be executed, in these little checkpoints. The sequencer could take the user's transaction, sandwich them, backrun them, front run them, censor them, and they can extract value from their users' transactions. So the question is this a potential business model? Is it the Robin Hood of layer 2 systems? Or is it an outright attack on the system? Now, MEV is getting very popular on Ethereum, and I took this screenshot a while ago. Miners are doing this now on Ethereum. They're extracting value from users' transactions, and Flashbots also help with that. So, is it an outright attack on the system? I think this is just a very subjective matter, and I don't have a strong opinion on it. Now, another reason why we have to trust a sequencer is that if the sequencer is honest, if they have a good reputation, and they have good behavior, then the layer 2 system is optimistically very fast. The sequencer offers the fast path for transactions being finalized. I give my transaction to the sequencer, they acknowledge it, and they say, yep, that's final, this is how it'll be executed, and then once I post it to the checkpoint, I'll notify you again. And then we can actually get if this is true, then we can have the Coinbase experience, but for layer 2 networks, because sequencers offer this rapid fast path for us. But if the sequencer can't be trusted, they don't have a good reputation, Or if the network just isn't set up to allow a sequencer to make that promise, then actually it's very slow. I send the layer 2 transaction, then I have to wait until the ordering is finalized on Ethereum. And if I have to wait for that order to be finalized on Ethereum, this is actually slower than just transacting on Ethereum. It's just very, very, very slow. Now, for value transfer, you probably don't care. But if you're interacting with smart contracts or DeFi, then you want quick finality. I want to know that I got my swap at the correct exchange rate, so I can then perform a second swap. So sequencers offer the fast path. So now we still need to consider who can be a sequencer and how are decisions reached. So we have to consider governance of the network and how transaction batches are finalized. How do I become a sequencer? Am I centralized? Is it proof of stake? Am I appointed? Etc., etc. And finally, the consensus protocol. How do sequencers reach agreement on the next set of transactions to be executed? Is it round robin? So is it Alice, Bob, Caroline, Alice, Bob, Caroline? Or is it some lottery system like, I guess proof of work's a lottery system. They win the lottery, they send a block. Do they have to do is it majority vote? Do we have to rely on, K of n sequencers to agree before they send the checkpoint? I think Polygon does that with their proof of stake system. That would really depend then, based on how you select sequencers and how you make decisions, whether we get the Coinbase experience or not in the layer 2 world. And the final problem is the mass exit problem. So this is actually a problem for the optimistic rollups or the plasmas of the world. So the issue is that if the layer 2 system gets compromised, and there is a situation where not all users can safely exit the system if they're entitled funds, then every user has the incentive to exit the system and get out ASAP. So what's a good example of this? One is a fractional reserve. The layer 1 smart contract has 100 coins, but the layer 2 system has 102 coins allocated to their users. The assets don't cover the liabilities, 100 coins versus 102 coins. Well, that will result in all the users racing out to get their money. Because if you're the last user to get out of the layer 2 system, and you've got those 2 coins, well, you'll perform a withdrawal transaction, but the layer 1 blockchain will no longer have those funds. If it doesn't have the funds, then you lost your money. So that's not a great scenario. So one's a fractional reserve. This could happen because of a bug, a fraud proof isn't processed, etc., etc. The other problem is just the data may not be available soon. So this was really a problem of the old style plasma protocols, where a checkpoint could be confirmed, but the data is not publicly available. And if the data is not publicly available, then you may lack the data to get, the actually process of withdrawal. You can't process a withdrawal, you can't get your funds out. So everyone's racing before that checkpoint gets finalized. So that is the max exit problem. It's just when the layer 2 system gets compromised and users have to run and get their funds out because they don't want to be the last one out. So now we have these really cool additional security properties. We have to care about extractable value, protocol liveness, and mass exit. And as you dive down this rabbit hole, there's just more problems and there's more goals that arise because commit chains are way more complicated than payment channels. But I hope you now have a better understanding of the layer 2 protocols. We've only scratched the surface and there's still so much more to explore. What I foresee in the future, and I've been saying this for I guess years now, is this will be the layer 2 landscape. We're going to have these ledgers. They could be layer 2 ledgers. They could be sidechains. They can be custodial ledgers. We're going to have this intermediary instant value transfer routing network, which could be Lightning. It could be Connects. And really, it's just used to synchronize across the different ledgers. If I want to, have funds on Coinbase, I want to perform a swap on Polygon, and bring my coins back to Coinbase. This payment channel network can actually synchronize that for me across multiple ledgers. So I foresee this is how everything's going to evolve. We're finally getting the layer 2 ledgers. We have this highly sophisticated, if not complicated, routing network. And now we have Ethereum as a settlement and the bridge layer. Because really, when you think about a layer 2 system, a sidechain, or a custodial ledger. Really what we're talking about is a bridge between Ethereum to that system. The bridge could either be, independent, the bridge could either, if it's a layer 2 system, the bridge needs to be convinced the layer 2 system's not compromised. If it's a sidechain or a custodial ledger, the bridge just needs to be convinced that the withdrawal can be processed, and that could be by an authority or something else. It doesn't care about if the ledger is compromised or not. But I hope you enjoyed the talk. Again, this is what I want to finish with. You're not building a layer 2 protocol unless you have this epic bottle in your hands. If you have any questions, I think we still have some time. We have, I guess, 20 minutes, so I finished a bit early, so I'm quite happy with that. GG, guys.
Thank you, Patrick. Yeah, I don't see any questions as of yet. I think it's because you were so very thorough and everything, which is great. It was really nice to follow along with all that. If anybody has any questions right now that are on, please feel free to put it in the chat, or you could put it in the ask a question. As well, if you are interested, we can, you're welcome to ask your question to Patrick yourself. Loic, am I saying that right? He says, thank you for the presentation. Thank you. This was really great, Patrick.
I was going to say, they can just ping me afterwards on Slack if they want.
Absolutely, yeah. And Patrick is available on Slack. If you have any questions, I know there's a lot to absorb. We also have the slides. Thank you for sharing that, Patrick. So yeah, hit him up on Slack afterwards if it suddenly comes to you. But is there just, for just like a takeaway for everybody who's here today, what would you say, Patrick, would be maybe the main thing to think about with layer 2 is something that everybody can walk away with in terms of this topic? Yeah.
So I think that the main highlight is when you consider layer 2 protocols, what you're really considering is the bridge between Ethereum and this ledger. Now, what makes it a layer 2 protocol is when Ethereum and this bridge has to be convinced that everything on that other ledger is valid and correct. If there's if it's compromised in any manner, then Ethereum will reject it and it will not process that invalid transaction, and then you can just withdraw your funds. So one good example of this, because I was reading this before this talk, was the Polygon system. So right now there's this debate on Twitter: is Polygon layer 2, checkpoints, commitchains, is it a sidechain? But when you dive into the code, the bridge relies on 2/3 majority of the proof of stake validators. So these validators come together, they sign the checkpoints, and they post them to Ethereum. Now, the important bit there is the validators that need to be convinced and not Ethereum. So it's not a layer 2 protocol in that sense. It's a sidechain. It's a proof of stake bridge with a sidechain. But that's really the difference for a layer 2 protocol. It's this bridge is the ultimate authority, and it should not rely on any other information other than that. That's probably my biggest takeaway.
Yeah, that's great. Actually, there are a couple questions that have come in. So could you take an example on how Uniswap version 3 works as of now? This is coming in from Amelie. She says, I know they migrated on an L2 layer.
Oh, yeah. So they're going to be on Optimism, I guess. So, Optimism's EVM compatible. So basically what you'll see is that you'll have this EVM blockchain on Optimism, and Optimism will simply post all the transaction data to Ethereum. So there's actually 2 steps to this. So for Optimism, and Arbitrum works in a similar manner. The sequencer will take the layer 2 transactions and they'll immediately post the data to Ethereum. This will guarantee the order of how your transactions are executed. So in the Uniswap example, you look at the Uniswap smart contract on Optimism, you sign a transaction, you give it to the sequencer, they'll post it to Ethereum, and that will guarantee how the order of your transaction being executed. So when that hits Ethereum, you can look at it and say, oh yeah, my transaction's been ordered, my swap was successful, and it's been complete. But the actual execution, Ethereum's not being convinced yet about the execution. You can just verify yourself that it's definitely going to be correct because you know exactly how those transactions will be executed. Later on, the sequencer will post a checkpoint. This checkpoint will then, confirm the execution for all those transactions. And then after 2 weeks, Ethereum will then be convinced that, your transaction was executed correctly. So that's probably the Uniswap example there, from start to finish. I hope anyway. But otherwise, it should just be like, transacting on Ethereum for the most part.
Okay, great. Yeah. And then we have another question from Leandro. He asks, is the biggest issue with Lightning Network the upfront collateral and the centralization that causes, or that it causes?
Yeah, I think the problem with Lightning Network is that it's sort of like cryptocurrency. People look at cryptocurrency, they see the word currency and they think it's a currency. When really cryptocurrencies are assets, it's a crypto asset, it earns yield. It's not really a very good currency. And I think Lightning has the same problem. It's advertised as a payment network. So everyone's trying to figure out how merchants can adopt this and enable payments for users. And really, it's not very good for merchant payments. We've just seen that with the example of a payment channel hub. It's much better for just routing value across different ledgers. And we're seeing that with the Lightning wallets are all custodial, and you're just sending funds from one wallet to another. You're not really paying anyone, you're just transferring value in a custodial setup. So I think the main problem there is use cases. And that is not really for payments. So most people don't need to set up a payment channel. They just need to send a transfer to someone who does have a payment channel, and they route the payment for you.
Gotcha. Yeah, and in terms of, so this subject is obviously, this is everybody is racing to be the ones coming up with the latest and greatest with obviously this is big on scalability, addressing issues around energy consumption, all that good stuff. So in your opinion, I know this is off the record, what do you think are the most promising projects or tokens out there right now that are trying to solve these, have an L2, if you will, solution right now?
So I think there's two answers to this. I think it's so I think in terms of being 100% layer 2 and going towards that goal, I think the current front runners from my mind would be, Optimism, Arbitrum, Starkware, although Starkware does have some trade-offs with their committee, ZK Sync. It's the usual lot. You're well known in this. But then you look at Polygon and they have a lot of traction, the tokens going to the moon. And they're not strictly a layer 2 protocol. So I think it's more to do with, do people care about these trust assumptions yet? Does it really matter if you rely on Ethereum security or if you rely on the security of another network, but you just have a bridge that lets you jump to it? And I think that's probably what we're going to find out over the next year.
That's a good point. So is it, so are people more concerned with you use the speed of transactions and getting that kind of solved, or is it also that issue of the security, which is equally as important? Maybe people are trying to solve both. What do you think about what I'm calling alt blockchain solutions? Because they're trying to bypass this issue, which L2 is trying to solve.
Oh, do you mean like Binance Chain and other EVM blockchains?
Yeah, isn't there one like Hedera Hashgraph or something like that where they're literally?
Hashgraph, I don't know.
Yeah, is that something that's?
I think their white paper was full of hexagons. I don't remember. No, so I think this comes down to different blockchain protocols. Curious. Yeah, there's obviously different blockchain protocols that allow to increase the throughput of the network. So almost like a DAG. So I think Hashgraph was supposed to be a DAG. Ava is a DAG. So that's really just optimizing on how do you propagate information across the network and how fast do people have to agree to that. It's just DAGs are just you just blast out blocks and then you go towards the largest weight of that tree. And but the problem there is, one.
Yeah, it's like a gossip model where they just basically. Yeah, and then they reach consensus, and then they're saving the energy of basically mining that kind of solution. Yeah.
So I think there is just mostly latency. It's just you probably get finality much faster, but there's the actual protocol. There's a lot more overhead involved in it, as in just messages going back and forth in the long run, more data to be stored. And then they just hit the throughput ceiling. There's only so many transactions you can send across the network that everyone else can verify in real time. And so really what you're trading off, the trade-off is throughput versus you can verify that the network's correct in real time. And that's just the bottleneck that everyone's going to hit. you know.
Yeah, right. Awesome. And yeah, and I think right now, well, with the latest release with Truffle, excuse me, and Polygon, I mean, that is something that Truffle is specifically focusing on, is that L2 solution. And that's great. I think that's
I
something that we
think
should.
Infura supports it now as well. Infura supports Polygon.
And exactly, and Infura too. And I think that's going to be a natural kind of connection between the two. I'm hoping for some. Well, actually, we're hoping for maybe some innovations in this hackathon potentially. Kevin Bluer, he had done a workshop on getting started with Truffle and was like hoping to inspire everybody to like build some plugins or think about some integrations there. But yeah, absolutely. So yeah, great. Well, thank you so much, Patrick. If there's any other questions, now's the time. Again, I know this is a really in-depth topic, of course, but it's great that we're thinking about this stuff. If you guys are inspired at all, we would love for you to, sign up for the hackathon. We can vet some ideas around this concept of L2. Of course, feel free to reach out to Patrick on Slack and continue the conversation. But yeah, this is something that we would love to innovate on more. And if there's also, please RSVP for our remaining workshops. Join us on the ConsenSys Hackathon 2021 channel. That's where we'll be posting replays, links to the workshops you can RSVP, as well as the sign-up form for the hackathon and all the details around that. There's some great prizes to win, so hopefully that's incentive too. Yeah, I appreciate it so much, Patrick. This really was a great workshop. I've got a lot of, I was learning a lot in this one too. So I appreciate that. Very thorough. So thank you again. And we hope to see everybody on the next one. Thank you, Patrick.